I'm going to start with like a little introduction of myself. I study Earth's ice sheets, and I got interested in this as a math student, as an undergraduate math student. I had the opportunity to work as an intern on a project about tipping icebergs, and that was really fun. It piqued my interest. I came back to New York and worked at the Lamont Doherty Earth Observatory, where I modeled the ocean floor around Greenland from gravity data collected by an airplane. I had the opportunity to do field work in both Greenland and Antarctica. And since becoming a graduate student, I've worked on some time series problems, some virtual reality projects, and my research interests have evolved to study not the bottom of the ice anymore, but the surface. I don't do this by myself. This is a picture of my advisor, Robin Bell, and I work with her and many other scientists and engineers on projects such as this one. This is the IcePod. There are very many scientists and engineers who are focused on new techniques for measuring the ice sheets, understanding how they're changing, and figuring out what causes that change. What are the physical processes involved in how the ice sheets are flowing, evolving, and losing mass. We care about these regions in the north and the south. Greenland is the northern hemisphere ice sheet. Antarctica is the southern hemisphere ice sheet. And together they contain about 90% of the world's fresh water. I've added the United States here for scale so that you can get a sense of how much ice is in each hemisphere. An ice sheet is a large area of ice that's in contact with the rock underneath, and it flows under the force of gravity by its own weight, sort of out from the center, out to the oceans. We care about these areas because together, if all of the ice melted, it would raise sea level by about 65 meters. And that would have implications for the coastline where most of us live. And as a background, to continue the background anyway, I'm going to talk about 3 ways that we know by measuring from space how the ice sheets are changing. So I'm going to show 2 videos. The first one, all right, here we go. So you're zooming in on a region in West Antarctica called Pine Island Glacier, and the first thing you're going to see is velocity data from the mid-90s. So you can tell that it's speeding up as time goes on. And so more ice is flowing from the middle of the continent out towards the ocean. The second measurement that you can make from space is height change. So as you go on in time, you can see, so red is thinning. And as you go on, you can see that the ice sheets are thinning, and they're thinning in the places that they're flowing faster. So those are two measurements that we can make to document the change. There's another one, also from satellites. This is a satellite that actually measures gravity, and from that we can infer mass loss. And red shows a mass loss, blue shows a mass gain. By the way, the glacier that you were looking at before, Pine Island, is right here in this area where we know that a lot of mass is being lost. So those are 3 direct measurements that we can make that shows change on pretty fast timescales. So I mentioned before that the ice sheets are grounded on bedrock. But around the edges where they're flowing out towards the ocean, the ice actually comes up off the rock and is floating on the water. And these are the areas that I study. They're called ice shelves. I've marked 3 of them here, the Larsen and the Nansen I'm going to talk about later, and then I've marked the Ross here because this is where I got to go a couple of years ago. And these 2 diagrams are showing the cross-section of, I like a diagram of what the ice shelves look like, and it's included the surface melting, which is what I study. So in the top panel, you're seeing a pattern where ice is being melted, the water's collecting into ponds, and then there are crevasses in the floating part of the ice shelf, or of the ice shelf. And the ponds can propagate these crevasses or fractures all the way through to the ice thickness and break pieces off. The bottom panel shows a different type of system, a different pattern where you melt the ice, maybe you've got some ponds, but actually the water can get transported long distances by rivers, and these can end up in waterfalls off the edge of the ice shelf. there are two examples, real-world examples of this. The first, you might remember, is kind of a dramatic event. The Larsen B ice shelf in West Antarctica had been stable for thousands of years. And if you look at this top image, you can kind of see there are very many ponds that are forming on the surface. There are thousands of these lakes. They're arrayed in a very special pattern. And in 35 days, a piece of ice around the size of Rhode Island disintegrated. And that's because of the way this process in this diagram, that the ponds are able to crack and fracture the ice. And if you have them arrayed in a certain way, you can get a disintegration event like this one. Recently, we've seen evidence for the other pattern shown in the schematic. So this is the Nansen ice shelf. And in this satellite image, you can kind of see that there are ponds here, the same way that there were in the Larsen B, but there's also a river that runs down, transports water across this shelf and empties it out into the ocean. And this is a picture of what that waterfall looks like. It's very impressive. And because everybody likes movies, I'm going to show you a movie of the waterfall. So the ice shelf is in the background. I'll play it one more time. You can see the waterfall falling off the shelf, and then in front of that is the ocean. It's covered in icebergs. So that's what these things kind of look like. And these two observations have led to this question: can rivers, by removing water, protect ice shelves from breaking apart? So I'm really interested in how the spatial pattern of water on the top of ice shelves can affect its behavior. And the way that I think about this is in terms of a total budget. So you could imagine that the amount of water that you melt should be equal to the amount that you store versus the amount that you remove. And today I'm going to talk about the amount that is stored. And I try to estimate this volume from satellite images. And I do this at an ice shelf in Greenland called Petermann Ice Shelf. So just to orient you, the ice is flowing from the bottom here towards the top. All of this is the ocean. There are icebergs, and it's flanked on either side by rock. Ice is flowing in from the side. You can see some ponds. Maybe this image is a little bit too small, but you can see some ponds here. There are also ponds all the way out towards the edge of the shelf. There are two rivers, one that runs down the center line. Actually, there are more than two. One main one that runs down the center line. There's a meandering one off to the side. There's another one here. And this person actually did kayak down this main river that we know empties into a waterfall. So fun or dangerous, I'm not really sure, but it happened. So to show you what the data actually look like, I just made a small movie of the area that was shown in the red box before, of how the water evolves over the course of about a month in 2016. So I'll play it a couple of times, but you should probably be able to convince yourselves that the pattern changes in time, and pretty quickly too. So you can see lakes that form, and then by the end there are far fewer. Some of them may be drained, some of them persist. I'll play it one more time. So in the beginning, there's water everywhere, lots of lakes. These disappear really rapidly. The river runs down the middle, and so I think looking at this, it's easy to ask yourself, well, are these ponds connected to the river? Is the river draining the water? How is the water moving? And there's clear evidence that it is changing from day to day. So looking at these images, as well as reading very many studies by other people, I'm not the only person interested in this question. This is a big area of research. I've kind of broken it up into patterns that I think we see and that might be important, that might actually like sort of define end members of a spectrum of behavior. So in Antarctica, this is my little diagram of what the Larsen B example would be. You have a lot of lakes. They're spaced in some regular way, and this is the type that could break an ice shelf. In Greenland, like what I just showed you, there are some bigger lakes clustered upstream. There are smaller ones that are downstream. There are fewer lakes here. There are other places in Antarctica where the lakes are much bigger, but they're concentrated in an area where you would expect a lot of melting. And then in terms of the rivers, both Greenland and Antarctica have these rivers that get all the way to the edge and end in a waterfall. And they have really similar shapes. They're kind of long and linear. We think that they might be there because of the way that the ice moves and also the way that the ice interacts with the ocean. There are also much wigglier rivers, and I'm not really sure. I don't think that they are controlled by the same process that makes the long, skinny ones. So a little bit about the data that I use. You saw some satellite data yesterday. I mostly look at Landsat images. So Landsat is I guess a platform that's been collecting imagery of the Earth since the mid-'70s. The repeat time is every 2 weeks. So every 2 weeks, the satellite's going to take an image of the same place on Earth. The pixel size is about 30 meters, so it's not very detailed, but it's good enough to measure the changes that I'm seeing. And it looks like this. So it takes measurements across the visible spectrum and then into the infrared. I use just the visible images. So each band is basically a black and white image of reflectance. Well, you turn them into reflectance values, and then you put them together, and you get images like the ones I showed in the movie. So this is multispectral data. You can infer a lot about the materials that you're looking at by investigating all of the bands that the satellite collects. So one of the things that I do is I take these images and I try to find out where's the water. If anybody is familiar with remote sensing, this water classification index is really similar to the vegetation index that people use to try to classify plants. So what you do is you take, in this case, the blue data and the red data, you do a really simple calculation, and you get a map that looks like this middle image. And other people have done this and partitioned the value or the range of NDWI values that you can get into shallow, medium, and deep water categories. And since I'm after water volume in this budget, this at least gives you a range of possibilities with a really, really simple calculation. The other thing you can do is, knowing what we know about how light interacts with water, you can come up with a physically based model that instead of using 2 bands, you just use 1 band, and you say, well, I know about how bright the ice is, I know how bright the water is, I know I can guess what an infinitely deep lake might look like, and you can get a map that looks like this one labeled depth from color. And you can see there are differences between these two, but they are both picking out the patterns that your eye would pick out in the visible image. I'm going to talk about some of the challenges associated with these, mostly in terms of the NDWI. What I do is I use this classification as kind of a heuristic for running this depth from color. But you can do one or the other or both. Okay, so the challenges associated with this. The NDWI classification misidentifies shadows as deep water. And just to orient you again, this is the Petermann Ice Shelf in Greenland. The ocean is over here. Ice is flowing from the bottom of this image to the top. This rock over here is a fjord wall, and it's casting a shadow onto the ice. These are crevasses, so there's water in here too. And I was actually really surprised by this, because I can tell what a shadow is, and you can tell what a shadow is. But if you actually look at the spectrum, like at the pixel values that are recorded here, and you do the NDWI classification, they're spectrally basically indistinguishable from each other. So this is something that will completely overestimate the water storage, and we need to take it into account. One way you can do it is by just saying, okay, I'm going to make a very conservative mask of how this shadow is, of where the shadow is cast, but then you lose the ability to analyze the nearby area. I've tried to cast the shadow by knowing something about the elevation, but actually I think the best way to do this would be to use some kind of machine learning and like image segmentation. I'm sure someone in this room could do it. That would be a much better way to go. So the NDWI also messes up with misidentifying different ice surfaces as shallow water. So it's also going to overestimate the total volume stored. These two images are of the same area. The first one shows a really bright ice surface, and it's very clear that this one is liquid water. There are some areas where if you have a lot of wind, the ice surface that is exposed is a little bit blue, and hopefully you can tell that the one on the the right side is overall a little bit bluer than the one on the left. If you ran the NDWI on this, you would end up with shallow water everywhere, and we don't really think that that's the case. This is a really difficult problem to solve because optically you can't really tell a lake that's totally liquid from one that just has, imagine like a really thin layer of ice on top of it. You would see right through that. You wouldn't know that it was frozen. And this is where satellite radar could come in and actually tell you about the material properties of the ice. But that involves incorporating a data set at a different spatial resolution, a different temporal resolution, and a fundamentally different measurement. So I think this is another interesting data science problem for someone in this room. The other thing is that the atmosphere influences the water storage volume estimate. And just to illustrate that point, we do a lot of different corrections in order to turn the raw data into a reflectance value that has physical meaning. And usually that involves a correction for what's happening at the top of the atmosphere. And when you do that, you get the image on your left. And I did a simple calculation for what the effect of the atmosphere might be, and then you get the image on the right, and hopefully you can see that that one is a little bit redder. If you remember, the NDWI incorporates the red and the blue, and if you were looking at the depth from color equation, I used the red band for that. So having the overall image a little bit shifted towards the red is a problem. And in order to solve this, you can use some ground truth data. But again, you want to be able to do this because properties of the atmosphere change every day. You'd like to be able to do this just based on the image so that you're not making assumptions about what the atmosphere was like last week and bringing that into the image that you're collecting this week. The last one is just trying to figure out what is a lake and what is a river. And this it doesn't have to be too difficult. It's the difference between a circle and a line. But the thing is that sometimes the lakes are elongated, and sometimes the rivers look a little bit broken up. So a river could actually look like a bunch of small lakes, and a lake could potentially get misidentified as a river depending on its shape. I think this is another possible machine learning problem or deep learning problem. I don't know. I have a vocabulary problem. So to bring it back to the original question, I'm trying to figure out how much water is stored on an ice shelf by looking at Landsat data. And hopefully I've convinced you that it's possible, but there are some challenges to overcome. I want to overcome these challenges by analyzing more satellite data, including ground truth data, and then possibly drawing on the expertise of people in this room. So I'm going to end with what I think is another much higher resolution, much more beautiful image of the Petermann Ice Shelf. Thank you to all of my collaborators and advisors, and thank you for your attention.